you ever seen? Aha, me and boys delighted. Lukey's boat's got a fine for Cuddy, me boys. Lukey's boat's got a fine for Cuddy, and every seam is chinked with putty. Aha, me boys delighted. Oh, together, aha, me boys delighted.
So happy Monday morning, everyone. What I like about this time slot is that only the serious students are here now. Dedicated ones. So I got a very interesting question about assignment 1. It says, huh? The first assignment for the course, quote, data visualization, states that students are not allowed to use basic charts like line graphs, bar charts, pie charts, and bubble charts, but should use, quote, more advanced visualizations instead. Could you name me some visualizations which you think are advanced so that I can understand what makes a visualization advanced, and consequently which visualizations I can use in the assignment? Is, for example, a 2D scatter plot advanced enough, or is it only sufficiently advanced if it's plotted in 3D? What if I select particular data which I think can be best visualized by a line graph more than anything else, as it is the most informative and aesthetically pleasing graph? Would the reasoning that selecting the right data to be plotted be good enough to justify the choice, it's a long question, of a line graph, or would you instead say that the line graphs are unacceptable no matter what? Perhaps Professor C wasn't smart enough to pick the right data for plotting, so would that approach make me smarter than Professor C and thus satisfy the conditions of the assignment? After all, to get rid of the data chaos and see any trend in the data, you can't really visualize 10 thematically different columns in the same chart, or can you? Lots of questions in there. Lots of implicit assumptions too, some very tricky implicit assumptions that are very dangerous. So the short answer to the question is no. And so let's look at this in a little bit more detail. Can you, what are the more advanced visualizations? That's what we're going to be talking about in this lecture and the next lecture and then all the rest of the module. That's what the whole module is about, the more advanced visualizations. So you can use any of the things I'm going to talk about today, or any of the visualizations offered by the myriad of tools, except for the pie chart, line chart, and bar chart. But basically, a more advanced visualization is something that's more than one-dimensional. Remember we talked about dimensions last time? So a more advanced visualization is more than one-dimensional. So this is a one-dimensional visualization of bar charts. The only thing that's changing is the height of the bar chart. Same with the pie chart and the line chart. There's only one dimension in the visualization. So anything that has 2 or more dimensions is considered. Okay, this one has color. Ignore the color. Ignore the color. So anything that has more than 2 dimensions is more advanced. A scatter plot is okay. It has 2 dimensions. You can add 3 dimensions to a scatter plot, or 4 dimensions, or 5 even. It's possible to do a 5D scatter plot. What if I select particular data that I think can be best visualized by a line graph more than anything else, as it is the most informative and aesthetically pleasing graph? That's an assumption. So that's an implicit assumption, yeah? And that might not necessarily be the case, right? And here's another good one. You can't really visualize 10 thematically different columns in the same chart, or can you? Yes, you can actually. And we're going to talk about how to do that. Right? So the idea, in my other things I'd like to add is if I said, please use bar charts, pie charts, and line charts, if you're allowed to use those, that's the only thing anybody would use. Yeah? If I said you're allowed to use those. So that's another reason. We wouldn't learn anything, really, if we were just using pie charts, line charts, and bar charts. That's another part of the answer. Another part of the answer is I don't want to be closed-minded, so I will let you include bar charts, pie charts, and line charts as extra credit in addition to the basic assignment. So if you think, oh, this is line chart is definitely the best way to visualize this, then you can include that as extra credit on top of the existing assignment. And then you present an argument that says, here's how I know that this line chart is the best way to visualize this data. Yeah, that's allowed. I will. The caveat of this is I get to look at the visualization and decide if it is the best way to visualize the data. So I get to disagree and say, oh, actually, there's a better way to visualize this, and it's this way. Yeah, so you can submit those things as extra credit, but I reserve the right to say, oh, there's a better way to visualize this. But yes, there are great times to use bar charts and pie charts. For example, in this assignment, you could use a bar chart or a pie chart to say, oh, I'm going to compare the number of females versus males that get cardiovascular disease, for example, and you have one piece of the pie for one gender and the other piece for the other gender. But that's not very exciting. I hope that answers the question. Any other questions about assignment 1? I'm sure there'll be more questions, and the beautiful Richard Roberts is going to be in the lab tomorrow morning. It's the attendance register to help with further questions about assignment 1.
The data on the website.
Yes.
Is not the same as the one that's listed, same as the categories listed.
Okay, that's okay.
Is it okay to just use the ones that are on there?
Yeah, you just use the ones that are on there, yes. Thank you for pointing that out. Are any of the things the same?
Most of them, it's just 3, 14, 15%. But
Okay.
then there's 2 other ones which are cancer and AMR indicators.
Okay, yeah, as long as you have some collection of data, that's fine. Another question?
My question for the tools. I have already visited all the tools, all the links, what is in the paper. But if I'm just studying to find where I can download the free tools for the IBM Mini Eyes. A part of this, there's a version is available, so I've already downloaded that for the 30 days trial.
Yeah.
But I cannot download this one, and I want to.
I don't know if the Many Eyes tool is even available.
Yes.
It comes and goes. Like sometimes it's available and sometimes it's not available. So you have to decide like, oh, is it available or not? I haven't looked like lately if it's still available. But you just use Google and put in IBM Many Eyes and see if anything happens. It might not.
The version is available at the website of IBM.
Mm-hmm. And you'll notice on the data visualization webpage, it's kind of impossible to see all the tools because on the data viz webpage, you'll see like 2 links to tools, collections of tools, and there are hundreds. There are actually hundreds to choose from. So you're not limited by just IBM Many Eyes, for example. Any other questions? So it's a real world assignment, and so you're running into sort of real world challenges, right? If I click on teaching and then DataVis, and then the collection here, it's really an impressive collection. Has anybody looked at that yet? It's a very impressive collection of tools. You can see I have the fastest laptop on the face of the planet. It might not, but
Try Safari.
yeah, I should try Safari. But see, that's how many tools there are. There are so many tools that it takes 2 hours just to load the web page. Any other questions?
Say if we wanted to use Plotly as an add-in to Excel, does that only count as one tool?
I guess you could count that as 2 tools if you wanted to. Yeah. Yeah, it would be still 2 tools. Yeah. Assuming you create one with just Excel and then plot LY. Yeah. Any other questions?
Yes, the assignment mentions very specific questions like what is the average size of each CCG. My question is, do we have to find an answer to that question?
No.
Or we can choose the questions ourselves?
You can choose the questions yourselves, yeah.
So each question is one visualization.
The questions are just there as examples. Like these are examples of some easy questions, and these are some examples of more difficult questions, but you don't have to answer those questions exactly. I'm happy to see that everybody's already started looking at the assignment and is excited about it. And another question. Maybe you can tell us your name before I need to know the names.
Greece. A slight aside from the coursework, I'm having difficulty accessing the notes.
Blackboard. So everybody's having, people having trouble finding the notes on Blackboard? Is that what I'm understanding? So I checked last night and I didn't have any trouble, but I suppose it's possible that some people are having trouble. Oh boy, if I can remember my login information is another question. So if I click on data visualization, and then I click on course material, I checked last night actually.
Module content.
Module content.
Top there.
Oh, right there, yeah. And then there should be a lectures. Something about lectures. Okay. I checked last night and it worked just fine.
It's working fine.
Yeah? Okay.
It's under course documents. You don't have.
Yeah, I don't know why the course documents is not here.
I do have it.
Okay. So if you click on course documents, there should be a link called course documents, and then it's in the lectures.
Use the wrong module code. CSC,
Ah, yes, you're right. It's the wrong module code. Well spotted. Extra credit. It's this one, right? Extra credit. Course documents. Yeah, there it is. So lectures, yeah.
Yeah, but I'm struggling to find the past exams papers. I cannot. Past exams papers.
That's under computer science student information. That's a separate. It's the past exams for this module will not be on this.
Okay.
this module's Blackboard. They're in a central repository called Information for Computer Science Students, something like this. Yeah, they're not in this particular spot. Let's see. They're in here, Computer Science Student Information. Another question.
Any third year students on this course don't have access to that course code. So we can
Okay, I need to sort that out. Okay, I need to write to Blackboard about that. What's your name?
that.
Ben? Thank you for pointing that out, Ben. Any other questions? Really? Okay, good. I can see everybody's excited about that. So we talked about data dimensionality a lot in the last lecture. And today we're going to talk about information visualization, just starting off a little bit with a little bit of information about color. So it's good to use color in your visualizations. If you're trying to map some value or category to color, it's good to use anywhere between 2 and 7 colors. That's not very many, right? 7 colors is not very many different colors. But that's the generally recommended guideline for visualization, because it's not such a great idea to use color to derive exact values. Color is good to compare relative values with one another. So we don't use hundreds of colors. Just as a side note though, the human eye can distinguish hundreds of different colors that the human visual perception system can distinguish. Are there any artists in the room? Anybody have a degree in art? I have a brother, Mike, that has a degree in art, and I remember one of his homework assignments was to create 300 different colors on paper. He had a mixture of like primary paint colors, and the assignment was create 300 different colors and lay them all out. Or maybe it was 200. Sometimes we see rainbow color maps. You may have seen rainbow color maps before. Those have problems, even though they're the most popular color map. If you ever look carefully at a rainbow color map, you'll see that the green occupies way more space than the other colors. It's not an even distribution of space. This is a fun one. Color perception depends strongly on the context, right? So what color you perceive depends on the colors that are next to it and around it. Has anybody seen that funky thing on Instagram? It's like you get a picture and then the question is it a yellow dress or a gray dress, something like that? Has anybody seen that? Was anybody able to see the different colors? Like see more than one, like sometimes gray and sometimes yellow? In that instance, it depends on 2 things. The colors that surround the screen. So you can get the yellow if you surround it with certain colors. Or if you look at another color before you look at the dress. So whatever you looked at just before you look at the dress changes your perception of the color of that dress. So it's what you see. It depends on what you see around the color and what you just looked at before. Here's a website. It's called colorbrewer.org. If you're trying to figure out some color scale, some optimal color scale, We won't go into this in detail, but you're welcome to check out that web page and explore it. But this will give good guidelines on choosing colors or color scales. This is related to what we just said about the color you perceive depends on the context and surrounding colors. So color can be used to strengthen boundaries. If I look at this rectangle, how many people, raise your hand if you think this rectangle is of uniform color? It's got a uniform color throughout every pixel. Nobody? So that's part of the illusion. Actually, every rectangle in this image is uniform color. It's called the Mach-Band effect. It's an illusion. So it looks like we're going from dark to light, a lighter shade of color, but actually this is a uniform shade. The only reason it looks like we're going from dark to light is because this is darker and this is lighter. And if the way to sort of bring out the illusion and see that it is just an illusion is to cover up if you were able to cover up this, even just doing that, it's sort of, you can start to see that it's an illusion. Right? So which color you see depends on the context. This one happens to be called the Mach-Band effect. This is just a quick statement that every device has its own color space. Right, so the number of colors that I can display on this laptop is different from the number of colors I can display on this laptop, is different than the number of colors that the projector displays, and that's different from the number of colors that appear when you try to print something out. Right? Anybody ever try to print out a photograph and have it looks a lot different, doesn't it? Yeah. It's tricky. Printing is still an unsolved problem. So just some more last tips. Grayscale lines are good choices for boundaries between regions or boundaries between shapes. Avoid dark blue for details and animations. It's very funny how often I see slides with a dark blue background and a red font. I see this all the time, even at university level with very smart professors, and I don't understand it, but it happens all the time. Avoid high color frequency. That means avoid too many colors, too many different colors, and too small of a space. And context and association are important. So what colors are surrounding the color you're looking at are important, and so on. And color can be used to strengthen boundaries. Okay, any questions about the first introductory? That's the end of the introductory lecture. So I know you're all dying to see the next lecture. So here's a printout of the next lecture. Is the attendance register still being passed around? So now we're going to see some more advanced visualizations. So we're going to look at some examples. We're going to look at how to visualize hierarchical data. And we're going to look at focus and context visualization. Those are the main themes. By the way, you can create hierarchies in your assignment 1, and I hope that some of you do create hierarchies in your assignment. This is just a little reminder. This is a map of all of visualization. And now we're going to start talking about information visualization. That means we're going to talk about ND data, which means data with an arbitrary number of dimensions. And there's no inherent spatial domain or no inherent space. So whenever you have that no inherent spatial data, the question is, well, how do we give it a space? How do we design some space to display the data? Right, and we talked a little bit about this already in data dimensions. So information visualization is dealing with abstract data, just like assignment 1. Although assignment 1 does have some spatial information in it, doesn't it? It has geospatial information, like on the map, space of a map. It's n-dimensional, so it has lots of dimensions, right, the healthcare data. So how do we choose a visual metaphor? How do we interact with the data? And how do we support exploration? Right, remember we mentioned exploration, analysis, and presentation. And in spatial data, analysis is very important. Fast rendering is very important. The challenges associated with it are slightly different. So if we are given some arbitrary set of data and we have to come up with some visual representation for it, how can we do that? Right? How do we design a spatial representation? How can high-dimensional data be depicted, like the student asks? Can we visualize 10 dimensions at the same time? And even if we did, would it make any sense? That's a good question for somebody's father, by the way. Does anybody have one of those dads that's like an authority on everything? Like that knows the answer to everything? Does anybody have a friend or a relative that knows everything? I have lots of friends like that and relatives. So next time you run into your friend that knows everything, I think everybody has a friend like that or a relative. The authority on everything. You ask them, oh, for example, hi Dad, how do you visualize 10-dimensional data? See how they react. How do we position the data in space? How do we integrate focus and context? This means how do we decide what's important from what's not as important? Maybe there are some bits that are more important than others. And how can we interact with the visualization? This is something that we talk about a lot in this module, in that interaction is usually left out of data visualization, right? You don't necessarily interact with a pie chart or a bar chart or a line chart. But in these visualizations that we're going to look at in this module, we see a lot of interaction. So the challenge is large amounts of data and large amounts of high-dimensional data. Sometimes we will select subsets of data, right? We'll use subset selection. Sometimes we'll put data into different categories or different groups, right? And sometimes we'll derive new data that is not in the original data, like hierarchies, for example. So sometimes if we're looking at hierarchical data, we might have problems related to deep hierarchies or very, very large graphs. How can we represent very, very large graphs? For example, a graph with 1 million nodes. How can we explore relationships between the different dimensions and variables? This is what I'm hoping you're going to do in assignment 1, by the way. And how do we support pattern finding? Some people define, has anybody ever thought about, like, what does it mean to be intelligent? Has anybody ever thought about that? We're sort of obsessed with that question in education, isn't it? We all want to be very intelligent. We want to be smart. It's like an obsession, isn't it? But what does it actually mean? Has anybody ever thought about what is intelligence? How do I decide if a person is intelligent or not, or smart? What is it? Anybody have any thoughts on that? I'm sure that you've all thought about this.
Just testing their IQ score.
Yeah, you have these standardized tests like, I don't know, A levels and stuff like that. In the US, we have SATs and GREs to decide if somebody's intelligent or smart and all that stuff.
Or having creative solutions.
Creative solutions. So has anybody ever thought, oh, an IQ test is not really a good measure of intelligence? Right? If you could say, oh, we agree, like Einstein's intelligent, right? Or we could take somebody that's famous and say, oh, they're intelligent. If I gave Einstein the SATs or the GREs in Chinese, and, and he said, please do this in Chinese, he wouldn't be so smart. So what am I rambling about? So sometimes we think, oh, the SATs and the GREs and the A levels are not a very good measure of intelligence. If that's true, then what is intelligence? Anyway, it's something I've thought about, and I'm sure you all have. One way to define intelligence, and it's an interesting way, it's the most interesting way that I've seen so far, is by pattern finding capabilities. So that's one way to sort of assess intelligence. How good is this thing or person at finding patterns? It's one way to do it. Right? So what are some generic approaches to deal with large amounts of data? Sampling or subsampling is one generic approach. Querying, this probably reminds you of databases, right? If you store data in a big database, you might write a query to select a subset of the data. Segmentation techniques are possible, right? This is where you divide all the data into different categories. In assignment 1, the different categories are kind of natural, right? It's different CCGs. Aggregation techniques are possible, right? Like summing, counting, frequency, minimum and maximum, right? And hopefully you're going to look at all of these things in assignment 1. And we're going to go over examples of all these things, by the way. Here are just some examples of some information visualizations that are a little bit more sophisticated than the typical line charts, bar charts, and pie charts. This is a tree map, and we're going to go over what it means, what a tree map is, how it's constructed, and how to interpret it. That the flow, a set of flow data has been segregated into different portions, right? Each one of these is a group, and all the members in this group have something in common. So it's a big, complicated data set. It's been divided up into different pieces. All the pieces have something in common, and then a hierarchy of them has been built, right? This is a spherical histogram. So we've seen sort of standard one-dimensional histograms before, but there are other kinds of histograms, and this is the same idea but laid out on a sphere. So we can integrate direction into the visualization and not just have them all standing straight. Okay, so any questions so far? The attendance register somewhere? It takes a long time to get the attendance register out here. Let's talk about hierarchical data and how to visualize hierarchies. That's one of our favorite things in life. So we have conventional approaches for visualizing hierarchies, things that you've all seen already before. You might not have noticed that it's a hierarchical visualization, but it is. Venn diagrams, tree maps, and we're going to look at some examples. Where do we see hierarchical data every day?
In any corporate industry.
Yeah, what's your name again?
Rishta.
Rishta. Oh, that's going to take some practice. In a corporation,
Yeah.
you mean like the management hierarchy?
Management. Yes, management.
Our favorite kind of hierarchy. You can see hierarchies in academics.
Yeah.
But where do you see it like personally every day? Like personally.
In family.
Family hierarchies? I guess so, yeah, I guess so. Any other examples?
Like music and albums and songs and artists.
Yeah, that's a kind of hierarchy. Music collections, yeah. You group them by songs by artists, and then you group the different albums by artists. So songs by albums, albums by artists, and then artists by genre or something like this. What's your name again? I'm gonna take
Reese.
Reese.
Daily tasks such as housekeeping and things for your academic work.
Okay. How is housekeeping a hierarchical data?
Because the different tasks involved in it belong to that grouping of data as opposed to academic work belonging to a different grouping.
Okay. I might be tempted to call that like a categorization rather than a hierarchical. But maybe you could arrange that as a hierarchy. The example I was thinking of is your file system. You all have a laptop or you all have a computer, and your files are organized in a hierarchy, right? You have every file is in a folder, and hopefully all the files in that folder are related somehow, and you can have a folder inside a folder, right? That's a hierarchy that you see and use every day. Anybody ever lose a file? I've lost many files because the file system that you usually use is not such a great visualization, actually. That window you see, that is the file hierarchy, and I have an example here somewhere, I'm pretty sure. It's not a very good, that's a file hierarchy. This is a hierarchical data set, right? Here's the top of the hierarchy, or one of this. Actually, you can't tell where the top is from this visualization. That's a visualization of a hierarchy. But I think the top is here, right? I click on some folder, and then I get the next level in the hierarchy, and the next level, and so on, until I find what I'm looking for. But there are some limitations to this kind of visualization, right? Anybody want to identify some of the limitations of that kind of size? Yeah, it's not very scalable. What if you want to visualize 100,000 or 1 million files? It's also, we also hinted at it already, it's very easy to lose things in this hierarchy, isn't it? Right, so that's a little bit of motivation for some of the more advanced hierarchies. This is usually how we look at hierarchies, right? In the form of a tree, right? A tree data structure. So this is a tree data structure. That's the root node of the hierarchy. Then there's the next level, and then so on. Here each parent node or each node can have a different number of children. It could be a leaf node. Here, every node has the same number of children. And this is our favorite example with the management hierarchy, right? That everybody knows and loves. That's our file system example that we're all very, very familiar with. This is an interactive hierarchy. So in this case, you only see one level at a time, and then you click on a node, and it expands to show the next level in the hierarchy. Then you click on this, it expands, and it shows the next level, and so on. And you can click on something again, and it will shrink and disappear. Right? And I think you've all seen Venn diagrams before. Anybody not see a Venn diagram before? So everybody has seen a Venn diagram. You can use Venn diagrams to visualize hierarchies. So this is the space of real numbers here, and rational numbers are a type of real number, and irrational numbers are a type of real number. And then integers are a type of rational number, and whole numbers are a type of integer, and then natural numbers are a type of whole number, and so on. Right, so that's a way to visualize hierarchies that I think everybody here is familiar with. But here's another way. Here's the Treemap example. So in this example, this is an example of cars, and this is using many eyes. But you see, I did it a while ago, back in 2014. So I don't know if many eyes is up and running today. But the cars, each car has been grouped into the country in which it's been manufactured. So the top of the hierarchy is car, then the next level in the hierarchy is country, then the next level is make, and the next level is vehicle name. So each one of these represents each node at the bottom level represents a vehicle name. And I tried to fire up disk inventory to show a visualization of my file system. So this is my file system being visualized with a tree map. Right, so there's all my some different folders, right? And every file is represented by a rectangle in this visualization, and every intermediate rectangle is a folder. Have you ever wondered, oh, where did all my disk space go? I've run out of disk space and I have no idea where it's all gone. Well, now we can see every single file on my laptop. So here's a file or a folder that's occupying 7 gigabytes of memory. So the size of the rectangle is mapped to how much disk space it's occupying. Right? So I could just delete that folder. And there are some more photos and so on. These are backup files here, I can see, because the information about the individual files shows when I interact with the tree map. I'm interacting with it, right? I'm moving my mouse over the different nodes, and then I'm finding out what the file is, where it is, and how big it is. All the information I want to know, right? I got to be careful about, too much exploration. I don't want to discover some file that should be a secret. But does everybody understand that example? Does that make sense? So that's a nice way to visualize a very large hierarchy, isn't it? It fills the whole space. Well, we can have it fill the whole space. I think we can click here too, and then maybe it does something. I think we can open just this folder in its own window. If my laptop was a little bit faster, right? But that's a very effective way. Has anybody ever seen this before? One person, two people? Nice. So you can download this for free, right? It's a free program. Anybody can download it and play with it. It's called Disk Inventory, right? So let's look at a brief demonstration about how to construct those tree maps. I used to have 2 markers. Oh, there it is. Oh, that doesn't help very much, does it? So this is the world's most simple tree map construction algorithm. This is hierarchical data. And then I can pick one like E, and then I can do another level, E, F, G, H, I, J. So that's our hierarchical data. And how do we construct the tree map? We start with a rectangle that fills the whole space, the whole screen, because that's one of the good properties of tree maps. They fill the whole space and make efficient use of space. And that represents the node, that represents the whole space, or the top of the hierarchy. Then with the next level we have B and C, so we can just do a divide and conquer. So now we have B and C. It's been split in half. And we can just recurse, so to speak. So now we have C. C has 3 children, so we can divide C up into three rectangles. A, B, C, D, E, and F. Can everybody see that? It's a little bit small. But that's when you get to sitting way at the back. Then we can recurse on E and divide E up into four pieces. 1, 2, 3. So E, F, G, H, I, J, and so on. Did everybody catch that? So that's one way to construct a tree map hierarchy or a tree map visualization. It's the most generic, most simplest, most naive way.
Does it matter if we start like dividing horizontally or vertically, or it's up to us?
What's your name?
Anna.
Anna.
Anna with an L.
Ella. That's a very good question. I'll ask, does it matter if you start vertically or horizontally? Was there any other part of that question? It was just that question. It does matter if you start vertically or horizontally. A lot of things matter So this is the simplest possible way to divide up the space, what I just did. But you can see that this could turn ugly. It's right now it's kind of okay, but it could turn ugly. Like what if J has lots and lots of children, right? Then J is going to get cut up. Well, actually, it doesn't look so bad. But J is going to get cut up into lots of small pieces. And it can happen in this scheme that you end up with if you have a funky hierarchy with rectangles that are very long and thin, and therefore a little bit more difficult to understand and visualize the data. So we can improve that algorithm. There are probably 20 or 30 different tree map construction algorithms and layout algorithms. We're not going to cover all 20 and 30 algorithms. But you can improve this. For example, there's an algorithm like you see in the slides. The slides don't show this algorithm. They show an algorithm that tries to squarify the nodes so they look more like squares. Yeah. Any other questions? Does everybody understand tree maps? Yeah? Tree map hierarchies? So it would be great to see some tree maps in assignment 1. Okay, we'll stop there if there are any questions.
Me boys didn't like